Thank you. Thank you for everybody here. And yes, great. And today I have a great honor to introduce you our speaker today, Dr. Maurice Roots, from NASA Goddard Flight Center, and he is specializing in air quality boundary layer dynamics. His work is driven by a mission to improve atmospheric monitoring capabilities to better protect environmental and public health. Dr. Rose process activities in active and passive remote sensing, in situ measurements, and multi-platform field campaigns. Dr. Rose earned his PhD in atmospheric physics from the University of Maryland, Baltimore County, UMBC, and his PhD work was supported by NASA Finance Award, which is a future investigation for the best graduate students and the James Fellowship, and also the NOAA NCASM program. He was investigate the influence and the formology of nocturnal low-level jets on air pollution in Atlantic. Dr. Rose began his career at Hampton University, got his Bachelor of Science in Physics with minors in nanoscience and mathematics. And during his undergraduate tenure, he was supported by Noah Holland's scholar and Noah Krasser. Today, along his research on NASA-led experiments, Dr. Fruits is a dedicated mentor committed to expanding opportunities for the next generation of environmental scientists. So that's where come Dr. Fruits.
I think it's better. How do I get rid of this bar here?
I think you can hide it.
Where's that at?
More.
What?
Or hide.
Floating.
Yes.
I think.
Yeah.
Okay, wonderful. Okay. Hello everyone. Yes, my name is Maurice Roots, coming from NASA Goddard, and I'm going to talk about sort of two things. One is what I do with Goddard and the group that I work with there, and then can you guys hear me in the back? Yeah. Is that better? Right here? Okay. So I'm going to talk about what I do at Goddard, and then some of my work that I do for research in conjunction with that, using the data sets, things like that. Okay, there we go. So I do a lot of stuff, and of course, like primarily, like at the beginning here, I'm a research scientist working with TollNet, and working on doing data analysis and engineering in the data and building instruments and going in field campaigns and stuff like that, and all of these different and hats. And I have something that you could ask me about in all of these departments, but that's what I mean about the different perspectives of what I have going on. And that kind of relates a little bit into how complicated it is for the stuff that we're working on, which is the complex planetary boundary layer in regimes that are sort of situated in this like coastal urban environment, which I'm sure you guys are very familiar with New York City being just to the west. For me, particularly, I was focusing on, Washington, D.C. and Baltimore region, as well as where I'm from, the Hampton Roads area. And like around the world, we see time and time again just a situation where you have an urban center and then some way to generate power for the urban center, and suburban to rural, and then of course all of that situated with a large port and on the water somewhere, and it creates this really complicated system in the boundary layer evolution that's influenced by the terrain and the differential heating between the different like surface types, and then the orography of like mountainous regions and things like that, as well as the synoptic situation of the particular region. And to study all of that, it's really important to have the multiple perspectives. If you're going after something like chemistry and dynamics, the multiple perspectives of the horizontal coverage of satellite remote sensing, and the in situ capability of balloons or aircrafts and things like that, as well as the ground-based monitoring or vertically resolved profiles of pollutants, and also column observations from the ground as well. And so that's kind of where I sit in hoping to understand the system, but also be able to assist in the management of the system as well. We do a lot of work with the stakeholders that care about the protecting the populations and commerce and things like that, and regulating emissions in this kind of regime. And so that kind of work looks like this. This is a big thing doing with the TOLNet group, which is the Troposphere Ozone LiDAR Network. And this network is a group of ozone LiDARs around the United States. And there was one site in Canada at one point. But sites around the United States, some are mobile, so we do deployments to different locations. And the connection to Stony Brook actually comes up from, we did a deployment from STAX in 2023, where my specific lab group at Goddard with the Tropos system, we deployed at Flax Pond just around the corner. And we're stationed there to collect this data for the whole campaign, which was us deploying some systems at the site for sort of creating a super site with like Pandora, and launching balloons periodically, coordinating with the mobile mass spec lab and things like that, and then our sort of sister sites across the sound to try and capture some of that plume dispersion from New York, and see the differences and apply some of the things that we have learned, or questions that we wanted to ask from the last time we did a campaign here, which was Listos. And so specifically, like this, in what is the goal of this super site was to sort of match all of these instruments together, so we can work with our profiles like this here of vertically resolved ozone from our ground trailer site, which is this is our trailer, 45 feet of lab space inside within benchtop ozone LiDAR, to understand that sort of 10-minute resolution temporally, and about 10-meter resolution vertically, where the plumes were situated, and then launch some sondes and see how that drifts, and match all the stuff up together. And what we do that, and then combine with things like high split trajectories and such, to try and piece out when, where, why we're seeing sort of these effects in the profiles. This one is actually a slide taken from another campaign that we did in Houston, going to another hotspot in the United States. A situation of the same that I mentioned at the beginning, of sort of a port city kind of dynamic, where this one was from 2021, I believe. And so, and that's part of the piece in that analysis phase. And showing you that slide, this is kind of the another view of looking into what Flax Pond data provides to us. And a lot of information, and I've coordinated on here the ozone sondes too. We've selected some sites, just like I showed on the previous slide, that we're hoping to have analyzed and matched up with some of the flight days from the aircraft that were also participating in the campaign, which was aromas, and partly in stats too. And that leads me to just put a little plug in here about where the data is located if anybody's interested. Perhaps we have a website and a little bit of a programmatic way to access the data set and things like that and work with the data. Do all kinds of things that you might find interesting. And I mentioned that because I also wrote the API for that too. So that's part of the other hats that I'm doing. So what we're looking for in the data set is better understanding of this picture right here. This little cartoon showing sort of the evolution of the boundary layer situated on the nocturnal time, or nocturnal period of the boundary layer. And of course, we're having, our ozone, and a lot of understanding has happened here in this like convective boundary layer phase. But where the LiDAR kind of shines, if the laser cooperates, is in getting the profiles during the nocturnal period, because we have our own light source, carry our own photons. So we can get a profile of the ozone happening here. And a small bit of chemistry on that, just being that, we're producing ozone roughly in a manner like this, where you have NOx and EOCs and a little bit of light and a little bit of heat, and you can create O3. Whereas in the nighttime, you're having sort of a reversal of that process, and you're eating away at your ozone and going to a point where you're decreasing quite rapidly as you enter this like evening transition period. And the associated with that is the dynamics piece, because I have to pay attention to both, is that you have a change in your wind vectors. And at the nighttime, you get to this rotation state because you reduced friction so much in the residual layer that produce something that we call a low-level jet. And this low-level jet, of course, because in the residual layer can be polluted, we end up with some effects where we see things like ozone increases down here at the surface because of polluted reservoirs injecting the pollution that's aloft of the stable layer into the stable layer because of the turbulence generated by the jet, and also transport associated with that, because these velocities here, depending on the terrain in the regime, can reach from 20 to maybe 30 in some locations meters per second, which has significant transport potential. And so in the mid-Atlantic area, as I've called it previously, I think I'm trying out Piedmont because this green shaded here is geographically known as the Piedmont region of the United States, situated between the coastal plains and then the Appalachian Mountains happening here. It creates sort of like a wedge that helps the genesis of this low-level jet. And we get this stream that follows in parallel to the sloping terrain here going this way. So that's kind of the sort of conceptual large-scale version of this low-level jet piece. So that's a little bit of the chemistry, a little bit of the dynamics piece, and then the case studies that we go through. So as I outlined before, those pieces of the profiles that we found interesting, we go in and we do steps like this, where either it's a large plume of ozone that's of interest to us or an exceedance event. And in this case, this is an exceedance event that I published in 2023 in Maryland, and I'm going to talk about that a little bit. And we started off by looking at the surface data. So this is from the surface, and it's from the EPA, and this is showing us ozone values in a tile plot, and things are color coded by the colors a little bit off there, but it's color coded by the level of exceedance here. And so it seems like it's typically outside of the ozone season, and that was interesting to us because when we look at the data set, it shows us at the surface that we're seeing in rural parts of the state that we're getting ozone concentrations that are well above what you would expect, well above the design value and have been exceeded in several years, that are in excess of some of the typical sites in the region that are associated with power plants and the urban center in Baltimore, and sort of also in line with DC, which is down here. And so that was kind of shocking to us, and that's when we come back around to the idea that there's a regional dynamics at play here. And that's sort of exactly what we found, and we were able to study that by using the same sort of concept of this sort of super site here, which is a combination of Howard University Beltsville, which has a lot of profiles and song launches and other ancillary observations that we use a lot, that complement to what we have at NASA Goddard, which is less than 10 kilometers away. And put that together to try and build a framework that we can apply routinely for the data sets that we produce later on, and give understanding to how we facilitate the measurements further. So this is just going back to remind about that location of generalized location of the jet going right through this region of Maryland. And that's kind of the piece that we see, and we showcase that by using profiles from the sonde, from the wind profiles from Wind Profiler. It's a 915 megahertz wind profiler. Our Tropos ozone LiDAR at Goddard. We have a ceilometer with us to give us a proxy at what the aerosol vertical profile looks like. And as well as I've used before, I don't think I have in this presentation, but the Aeronet and Pandora observations to kind of understand some more about the spatial extent and timing of transport, and as well as with the satellite observations. So back to that nocturnal piece that I mentioned, and then this is a plot showing you exactly what I mean about these increases in ozone at the surface during the nighttime period. So this is during the onset of the jet that was observed during this day, and we see really strong increases. And at most, which is directly in that path of where I showed you that jet at South Carroll, 20 parts per billion increase, in which is kind of amazing. This is, I think, one of the strongest cases that has been reported for the mid-Atlantic jet so far, and that's sort of matched and fed from this polluted residual layer above, that then comes back around from some synoptic forcing that pushes this wall of ozone across the state to eventually exit later through the Appalachian Mountains. But this is feeding in over in its height, not just at the surface, but sort of in a column around 90 parts per billion. And that was quite amazing to see. So we using the profiles of ozone on the top and the aerosol proxy on the bottom. Sorry. Is that green?
Yes.
Yeah. Okay. So with these colors, yeah, there's sort of green towards maybe almost yellowish here is higher concentration. This is a 1064 nanometer salometer, so this is a pretty good proxy of where the aerosols are located vertically. And then above, this is the ozone lidar that we have at NASA Goddard. And this is a nod to what I mentioned before about when the laser cooperates. So we kind of missed this one during the onset of the jet, but we did have a song launched, and that's where we can identify that vertical profile of ozone. And it's very faint on this screen, but right here is where that polluted layer is located, and you can kind of match that up with this inflection point in this band of aerosols here. So I kind of just mentioned most of this, but a little more context in that this is something that's associated with smoke, and we know that from the trajectories that we did that I'll show a little bit later, but also the intrusion of some very dry air at these levels that match up with the pollution that we're seeing incoming. And so this piece that we bring in this is from the 915 megahertz wind profiler, and this is the low level jet, and this is being shown from the star on the map that I showed, which is sort of this supersite. So we have the wind profile here, which is indicating to us some really strong downward velocities from the vertical velocity component here. Consistent wind direction, noting to us in the same consistency of the jet and the overall timing of the arrival of the core, which matches up to the same time as the inflections in the surface ozone during the nighttime, those large increases that I noted too. A little note to some of the other things that seem evident in this profile is the potential occurrence of downslope winds that's been noted before by a few other researchers to occur in the Appalachian Mountain region. And then this extremely high negative vertical velocities occurring at the time of that sort of wall of ozone that I mentioned coming through the region. And so this exceedance days seems kind of to be a mix of all of those events happening together in sequence. And starting from wildfire smoke from some fires, a chain of fires that was actually burning in the Canada region, the region of Canada that's above Minnesota. And this sort of trajectory is showing you the before, so where it came from, and then where it's going, and we match that with the AOD observations from MODIS each day. And by MODIS, I mean Terra and Aqua. And so we can sort of track that plume moving through the region. And the area that we're interested in, and I've shown on other plots in Maryland, is this black circle down. And to put it all together, the kind of analysis that we try to do and take with us is the ability to understand, at least at one site, to capture some of the temporal evolution of what's happening in the boundary there. And we're working on now and trying to bridge that into being able to do this at multiple sites, or at least transfer some of this understanding, especially in the winds, to ancillary sites that might be downwind or in separate locations for network logistics about understanding the ozone and the aerosol vertical distribution. So we can extrapolate to the spatial distribution and understand when, why, where exceedance events and just high ozone in general is occurring. I think there would be last slide, yeah. So I'm gonna stop there. I have a whole bunch more slides if you would like to ask questions about anything, but
Thank you so much. And you have so many questions. Anyone?
So I'm also a bit, surprised about this ozone exceedance when you have this low level jet coming in. And I would have a chemistry perspective to that. Is it because you have continuous processing of ozone? You go maybe from a NOx limited regime outside Baltimore to a more VOC limited regime, or is it during the plume in the low level jet that contributes to additional ozone at that level? Or do you think there is something else going on? I mean, on Long Island, we have this problem, or we have some of the worst ozone here out east.
yeah,
Because the plume goes over the northeast, over the city, over Long Island. We know it since the 70s. And it is because we go through different VOC NOx limited regimes and it just piles up. And in the evening here, we have higher ozone concentration than the people in the city.
mhm.
And so I'm wondering if your low level jet is doing something similar, that it brings in, and as the sun is up, it already starts processing what is in the residual layer at night.
Yeah,
It can just start on, but then you go over, well, I don't know your region well enough, but I think outside Baltimore it's likely greener. And then it comes into Baltimore. I don't know. So I'm just speculating.
yeah, it's a lot of forest around Maryland and also even more in Virginia.
So I'm just wondering if you folks have thought, this is more dynamic picture almost. That's really nice, actually. But if the chemistry could change, or what?
Yeah, so the chemistry piece, I'm really to answer that question, I'd like to sort of like fly in it and see what happens. I asked about that before, but it's been a rough year. I think that the jet as a mechanism can influence what's happening at the surface in a few different ways. Like, so in one is the transport and like what regions it's like going through. But I think also that sort of what's in the residual layer in that location can also be sort of kind of like bulldozed into like it's an intrusion into the stable layer. So there's a lot of different pieces there. And there is some discussion and about what the interplay may be in like the Bay Breeze concept as well. Like if the Bay Breeze is happening and pushing some sort of further cooked air back into the pathway of the jet as well. But these are just sort of ideas on things to like propose as sort of mini campaigns to try and study at the moment. So we don't really have the data to definitively answer in either direction at the moment. Yeah. But if you have any ideas on maybe how we could do it, then please, like.
Well, as I get older, I think I understand the planetary boundary layer less and less. And so I think the chemistry is easier than the dynamics going on. Exactly what you say. You have a sea breeze, and you have maybe a low level jet, and we don't even know exactly what is a residual layer, where's a mixed layer, where's a border. It changes every night. I mean, it's suddenly I have to pass the ball to the dynamicists again, because I don't want to do that because I'm a chemist, but that's really the case. I mean, the dynamics of the planetary boundary layer is really fascinating.
Yeah.
Complicated.
Yeah.
Especially then if you have something like Manhattan, we struggled with that last year. It's so complex, the heat island effect, the buildings.
Yes,
I mean, it's just like as soon you have an urban environment, things get so complicated
Yeah.
as well.
That's
Anyway, I stop here.
I mean, you mentioned the urban heat island too. That's another big thing that itself sort of builds a obstacle for the flow of the wind regime. So that's another thing that's sort of in question, maybe from this past summer with the Courage campaign we had, that we might be able to piece at that. Although Baltimore is there is a heat island that's there, but it's nothing compared to some places and how that might manifest.
Well, thanks for a great talks. I guess I have two questions. One is, I was just wondering if you could just kindly go through this figure again, since that's such an important piece of the talk. I mean, I understand the first one is ozone, the second is aerosol scattering. What are the three?
Oh, so this one in the middle here, this is wind speed,
Uh-huh.
and then this one is wind direction,
Okay.
and then the last one is vertical velocity.
Okay.
Yeah.
And then, yeah, thanks. And then the question is, I mean, if I just look at ozone and PM and the aerosol, I mean, they correspond really well here, right, at this event, but then I guess not so much in the first part. I'm sorry, maybe you already talked about this, but like, why?
Here, right here.
Yeah.
Oh, yeah. So I think that this the bulk of this smoke plume is from the transport that arrived at this time, and
Okay.
there's a little bit from before. Some of this is, yeah, it's a lot to do with the colors. So there is some resemblance, like this region here is matching up with the tail of this region here.
Okay.
I should probably make a plot that's sort of like that, like a and a agreement or like collocation in the time height axis of them. But there's, if you remove some of this noise ish, then variability in some of this like striping patterns here, you do see the same shapes arise.
Okay.
And also you also have a difference on the signal to noise ratios, right? So with the ceilometer, you don't get as much clarity that you could as like a higher powered LiDAR. And so there's like a little bit of like a smearing that happens in the profiles, which is like sort of contrary to the resolution that you get in the ozone LiDAR, but the shapes do match up. It's just about the signal that's there. You just have much more signal clarity later on in the day.
And how do you determine, like, this is mostly wildfire smoke contribution? I mean, I understand there is the trajectory analysis and everything, but like, what about the other background local sources?
Yeah, so we well, for one, the amount of ozone that was observed is sort of not possible with the local emissions, and then also the scale of like seeing that sort of wall progress across the whole state, and starting in basically out in the ocean, and then moving in like across the eastern shore and then across Maryland. So there's the dynamics piece of that, but then chemically we looked at the species that we could without the auto GC. Those don't turn on until the ozone season. So the speciation of everything, we don't have it because they literally don't turn it on until it passes into the ozone season. But before that, we correlate that the timing matches up also with like carbon monoxide and things like that.
Thank you.
It looks like wind speed and direction, this cycle of wind speed direction are quite important. Could you just elaborate What's what you see in the Meriden or the cycle of wind speed and direction that we see there.
This cycle here?
That's the best direction, correct?
Yeah, this is direction. Yes.
You see. What's
So
what's happening to wind speed, for example?
what's happening to wind speed? Oh, the change in colors here?
Yes.
Oh, so this is to the dynamics of what's forming the low level jet, which is still not finished. We're working on it, but the sort of maximum of the cycle in reducing the friction happens at this timing here. So you're getting like once the sun goes up, right, then you get to a certain point, which is here, and that's your maximum wind speed. And that also sort of decreases like with height as well. It kind of,
So a lot of vertical shear.
yes, yes.
Yeah.
What other part did you want me to refer to in?
Why is direction important?
Oh, the direction? The direction is important because the low level jet should all, the wind in a certain area, the width of it, maximum width is not been observed, but we can estimate it's like from the beginning of the Appalachian Mountains to the beginning of the Chesapeake Bay should all be in the same direction. It should create like a stable corridor to flow through. Yeah, so this should all be coming from the southwest.
From the southwest.
Yes.
Okay, and then how about later? Where's it coming from?
Oh, here?
Yeah.
So later, this is coming from the east.
Northeast.
Yeah, northeast and east, and that's sort of
Okay.
like this right here. This movement across the map is a little small. I wish I could blow it up, but if you follow like this green line here, it's the same coming down from like through like New Jersey.
Okay, so
And
northeast.
yeah, and then you see that in the surface too. So this gray line site here is at the top. This is the most northeast point of Maryland. And this one, there's not even really an increase during the nighttime here because it's just the boundary layer completely is just full of ozone the entire time. And this is also not in the jet corridor as well. Yeah, and that's kind of this arrow here, but so that's that gray site. And then New Jersey would be like here, so this is okay, and it comes this one. Yeah.
Thank you.
Going back to that last slide that you showed,
Yeah.
that in the second panel. The question I would ask, and I think you may have already provided the answer, is that abrupt increase in the aerosol scattering, and it's sort of uniform with height, which means you've got well mixed. Is that due to transport or local formation?
This is definitely due to the transport. And so it seemed evident to me that before this, it's local. And local with some increases that are a production slope that's higher than normal because of the influence from the jet beforehand. And so if I go back to this spot here, that's sort of where I get that from. So this slope of increase is not typical. And so we see a lot of that should be a lot of production here because of the precursors that it mixed in from the night before. And so all of this is local until that arrival happens. And then you see that sort of like wall that you push across.
Yeah, that wall is striking.
Yeah. So everything until then is local because we had some intrusion in the stable layer before, mixed with the local production naturally. And then you see this wall in the
Best trace of word. Small.
Okay, and in one of the earlier slides, there was an intriguing formation.
Well, which,
Keep going back.
okay.
They're almost at the beginning.
Oh, yeah.
I guess it went by too fast. Go forward slowly. It's on the right side.
It's like replay sport.
Yeah. Groundhog Day. I'm sorry, no, that's not it.
On the right side.
Oh, it's gone. There was a persistent low concentration of something layer that extended across a figure.
Oh, sounds extended across the future.
No, it's after this for sure.
Yeah.
I'll never find it again.
There's 100 slides in here.
It's gone.
Yeah. I don't know.
Okay, sorry.
That's okay. Persisting.
Ask the.
Yes, I'll question.
Oh,
I think so.
Yeah, we will come back to these slides eventually. Just on the final slide, sorry again.
No
So this, I don't think we know tons about wildfire impacts on ozone still. That's
Yeah.
I think an open-ended question. And don't really, I don't really know the answer to, but like, so I think it seems like, at least that's my impression on the literature, is people seem to believe that wildfire smoke impacts on ozone are through two pathways. So one is, obviously you had a very high ozone formation near fire, right? And then this part of the ozone just directly transports to downwind area, or maybe there is a little bit chemistry related to pan or those kind of stuff, but that's one of the mechanism. And the other mechanism is, of course, you also have high levels of VOC and NOx near fire, and then both of those precursor transport downwind, right? And then it seems like the NOx would get transformed or washed up, deposited really quickly along the transport. You end up very quickly with a very VOC rich pool, and they can mix with urban plume that is high in NOx and create ozone. So that seems like the two kind of mechanism people talk about wildfire impacts on ozone.
Yeah.
It seems like the data here seems to suggest the number one mechanism, like the ozone directly transport to those downwind area.
Mhm.
Does that seem fair to you?
I would say so. I mean, we're detecting the ozone still being present, and then also getting to the ground at its sort of final destination. I wouldn't count out necessarily that I'm like maybe either of those are entirely like separate. And then another thing of interest to me is like sort of in route transport and like what happens there in terms of the chemistry. Hopefully we can have an answer to that at some point. To make it more complicated, in this case, there are multiple fires sort of like lining up and what looks like potentially mixing together when we check some of the other LiDAR profiles, and some of the ones that have a higher vertical extent. We see that there's layering in the smoke layers as well. So there's like, I think this one had like 3 different smoke layers. And then I mean, in between the intermittent sites, we don't really have an idea of what exactly was happening in there. And then the back trajectory is over, I think, 48 hours. So in between that, the sun is turned on, and but then there's a whole bunch of radiative transfer and chemistry that happens along the way. I have no idea. But I would say that the ozone was transported as well. Maybe it could be that chemistry also happened along the way. But definitely in our region, it was from the perspective of Maryland, that ozone was transported and traveled with.
And just to make sure I understand, that was a really nice. So one of the strong evidence to support this is ozone derived transport is you also observe high ozone through the transport pathway.
Yeah.
Is that what you guys saw?
So for this case, our LiDAR observations are limited, but we have further observations from like the whole transport event. And we do see the evidence that the ozone is in there, that's in that layer. And so from the song that's right here, right? So that's in situ. It went through that aerosol layer, and it's measuring ozone in a chemical way where, it's potassium iodine plus ozone equals measurable signal, right? And it's being detected. And we have more songs than this that show us that what we conclude is that same layer is sort of streaming it into the region, yeah, for a couple of days.
Thank you.
So I'm glad you gave us a lot of time for questions. I had a kind of a broader question, almost science politics question. How do you justify a program like this to NASA management?
There's maybe three ways. Way number one is sort of the history of why TollNet exists, the Tropospheric Ozone LiDAR Network, because in the Clean Air Act, they mandate that NASA has to study ozone, and that was for the stratosphere, right? And so we kind of built a bunch of LiDARs to study stratospheric ozone, and then it was like, well, we can also do this for lower altitudes too. And then NASA trying to, in a certain time period, collaborate with other agencies and stuff, and then be a support for like NOAA or like the EPA becomes an asset to have an instrument that does this for something really valuable, like an ozone profile, and support in that kind of way. Then the second way is through the avenue of there's never been a ozone LiDAR in space, really, from NASA, right? So we developed this technology so that it can be eventually put into space, so we can do global observations of getting ozone profiles, and then that goes back into improving model capabilities for NASA's like huge modeling suite of GMAO and the GEOS model, which gets put into reanalysis and Merit2, which is all over the world, and specifically for like weather forecasting, things like that. And then a little bit of the third way, I don't know, but it's this is one of the only networks like this that exist in the country, and very few across the world. So it's a novelty to just even have it. Which,
well, I commend you and your team for successfully, at least so far, persuading NASA management to support such an activity. I think the second one is perhaps the strongest argument. Well, if we're going to put something in space, we have to test its capability. And I'm not sure where it would be most valuable. Would be on a platform like like where the AVHR is, something like that, which is only gonna get you snapshots for the day. Geostationary would be great.
That would, I mean, geostationary would be a really interesting engineering problem for that. Because just the way that we build LiDARs right now, we wouldn't even be able to support that. You have to redesign sort of the whole instrument. I think the direct path is definitely like a new and improved Calypso type of thing, where you have like a beach Sorel technique, and then you throw on some channels to do the dial ozone retrieval. Geostationary would be really cool if you could sort of like an ozone mapper LiDAR thing.
Okay, thank you.
Any other questions? All right, thank you so much, Dr. Lewis. Thank you for